So in my last lecture I discussed about Hilbert Matrix and approximating a function using a polynomial function, mth order polynomial function, and what we saw that we get this Hilbert matrix which for large order polynomial is highly ill conditioned, difficult to invert. Well, the problem is not different if I just passingly mention. See, yesterday we saw that we had this function ft which belonged to set of continuous functions, and then maybe we took some specific thing here 0 to 2 pi, and then ut which is function ut which is this, and then we had this approximation and then we wrote the normal equation and said that particularly when you pick this to be a polynomial, that is when you pick this to be alpha 0 plus alpha 1 t plus alpha 2 t square, for this particular case I showed that you end up into this Hilbert matrix, and this Hilbert matrix is trouble inverting. So in principle, though you get an equation, you cannot solve it properly because of ill conditioning. Now ill conditioning of a matrix will formally define a little later. Right now all that I would tell you is that the eigenvalues of this matrix, or singular values of this matrix to be very precise, singular values are eigenvalues of A transpose A. Eigenvalues or singular values of this matrix, the smallest one and the largest one are far apart, and that causes problems in computations. Now this is when you are trying to approximate the entire function. Suppose you know this function, instead of knowing the function, knowing the entire function what it is and trying to approximate it using a polynomial. Suppose you know this function values, you don't know the function, but that is a more practical problem in engineering. You just know function values at different points. So t1, this is t2, and so on. So tk, and in general you know value of this function at several points. So these values will be u1, u2, uk, un, okay, u1, u2, uk, un, and then at each point you will write this equation, that is approximation or uti is equal to alpha 0 plus alpha 1 ti plus up to alpha m ti to power m. You get these equations. Uti is nothing but ui. This is nothing but ui. So uti ui, okay, this plus error I, okay, and I going from 1 to up to n. You have these equations, we have done this earlier, okay, and we get this matrix, A matrix. So we will get this huge A matrix. So this will be 1 1 1 t1 t1 t2 tn up to t1 raised to m t n raised to m, and alpha 1, alpha 0, alpha 1, alpha m is equal to u1, u2, un. In this case you have this equation, you are trying to fit a lower order polynomial, say 10th order polynomial, and this n here, number of data points is let's say 1000. So you are trying to put a 10th order polynomial in 1000 points. Okay, you know this function value at large number of points. Simple example, Cp versus temperature. Okay, I know Cp values at many temperatures in some range. I am trying to correlate. I'll get something like this. There T will be temperature, okay, in that case, and then U1, U2 will be Cp values, and of course you have this error coming up here. So this error 1, error 2, error n, this vector will add here. So this is my A matrix, this is my A matrix, okay. So my A matrix, and we have solved this problem. We know that the solution, the least square solution is given by the least square solution, that is alpha least square is A transpose A, or I'll write it in a little different way. So this is A transpose A, alpha least square. Well, I think we named this as theta, right? In the earlier this thing we have called this theta, so let's keep calling it theta. So theta least square is equal to A transpose U. U is all the values of dependent variable, which you know. Okay, we know this. Now this, as I told you, is nothing but the Hilbert matrix. This is nothing but the Hilbert matrix. So this actually, what you can show, that this matrix in this normal equation will tend to Hilbert matrix. This is not Hilbert matrix. In the earlier case, we directly got the Hilbert matrix. If you have a large number of data points, okay, what you can show is that this matrix, the proof is just given here. I am not going to write it down on the board. This matrix will tend to Hilbert matrix. So for large values of see A transpose A, this tends to 1, 1/2, 1/3, 1 by m, 1 by 2, 1 by 3, 1 by 4. Okay, for large number of data points here. Okay, this particular matrix A transpose A, okay, you can look for the arguments here. This matrix will tend to this matrix, which means, you know, basically if you want a good approximation, what will you do? If you want a good approximation, you will take more data points, which is logical. Okay, if you take, instead of taking 100 data points, if you take 500 data points, you will get a better approximation. Okay, get a better approximation. But as you take more data points and try to fit the polynomial, this matrix A transpose A will tend to the Hilbert matrix, and Hilbert matrix is difficult to invert because this is a ill-conditioned matrix. Because this is an ill-conditioned matrix, we have a problem that we cannot get reliable estimates of theta. Okay, we will not get reliable estimates of theta, and because we cannot get reliable estimates of theta, approximation that you develop, say 10th order or 12th order, is not a reliable, is not a reliable polynomial approximation. A better way here would be to use orthogonal polynomials. Instead of using orthogonal polynomials, we will make this matrix. There are slightly different ways of constructing orthogonal polynomials for the discrete data case, which are discussed in the notes. So I am leaving it for you to read, but the idea is that if you use orthogonal polynomials, then this difficulty can be avoided. There is something that we already have discussed is how do you use least square approximation for fitting certain kind of correlations in chemical engineering. We discussed about Sherwood number correlation, or we discussed about Prandtl number, and Nusselt number equal to Reynolds number raised to something, and if you take a transformation, then you can linearize that problem and then solve the problem of estimating constants in these correlations using linear least square. So that we have already seen. So we have already seen one application of linear least square in approximation. Okay, so right now when I am doing Cp as a function of temperature, I am trying to approximate a continuous function using a polynomial function. This is one common application. You have some algebraic static map, and then you are trying to approximate using some other known functions, and the problem is transformed to estimating this theta. Okay, and we also saw in any general Hilbert space how you could construct the normal equation. I am uploading extra problems today for least squares, and so you can start looking at the problems where you will see a lot of engineering applications where you'll be using these squares. Now, one of the things that I promised to you is that we will now move on at some point to solving boundary value problems or partial differential equations using this method. Well, that's what I am going to do next. That is, see how I can apply this method for solving a partial differential equation. So now I am going to use the ideas of least square for constructing a solution of a boundary value problem. Okay, so right now I am going to restrict here to showing you two methods. One is method of least squares for a boundary value problem. I will not show explicitly an example of partial differential equations. I will also talk about a variant of it called Galerkin's method. Now, these two methods, though we'll be looking at them very briefly right now, we are not going to look at the details of this beyond a point, because these methods become very complex, and what actually this is actually, we are getting into the method of finite element. Okay, if you have to actually implement this, you have to get into method of finite element, and finite element methods are fairly complex when it comes to computer implementation. So it will go beyond the scope of this particular course. I have to stop at some point, problem discretization, and move on into solution techniques. So I am just going to give you very brief introduction, not really complete introduction, but at least the philosophy of this problem discretization, that is, say, boundary value problem. How do you discretize this using least squares approach? Philosophy will be clear. We will not go into the details. Okay, so details will be, I mean, if I have to get into details, it will take many lectures, and we have to move on and do other things other than just problem discretization. Okay, but this once we do this, it sort of completes the picture. We have three different ways of problem discretization. One is problem in this, particularly here I am referring to boundary value problems or partial differential equations. We discretize using Taylor series approximation. We discretize using, second is interpolation. We got collocation methods. Okay, third is this least squares. Okay, we get this finite element method. First is finite difference. Don't confuse. Finite difference method. Then we had orthogonal collocations. Then we also had orthogonal collocations on finite elements. Okay, and this method, but that basically is interpolation based method. And the third one is this least squares method. Interpolation, we want a polynomial to pass through every point. Okay, that is the difference. Approximations, we are trying to fit a polynomial in some least square sense. We don't want the polynomial to pass through every point or the function to pass through every point. Okay, so let's look at this method of least squares for solving. So this method is called as minimum residual method, and well, why can you solve a problem using optimization? And just to give you a little bit of a background before I move into least squares. Okay, we will revisit what I am doing right now on the board again, but I am just preempting something. See, we know how to solve Ax equal to b. Right now from your undergraduate, how do you solve Ax equal to b? Gaussian elimination? The best method you know is Gaussian elimination. You do, triangularization and then solve in the reverse direction. So that's one of the most efficient methods that we know. Can I use the ideas of optimization to solve this problem? Okay. Now let's see whether we can use the ideas of optimization to solve this problem. What we wanted in optimization, we want to minimize something, okay, and the minimum should be the solution, okay. Now let me take this before I get into this, let me say that I want to solve Ax equal to b. I want to solve Ax equal to b, okay. I want to solve this exactly, okay. I could say that, well, this problem is like saying that, let me define an error vector. Let me define an error vector which is Ax minus b, Ax minus b. Everyone with me on this? Okay. And then I'll define an scalar objective function, okay. I'll define a scalar objective function. So my scalar objective function is going to be, now, well, what I am going to do now is very, very similar to what is happening here. So this is my error vector, this is A theta and this is u, except in this particular case we had this matrix A was tall matrix, it was not a square matrix. Right now what I am writing there is a square matrix, okay, square matrix. So I want to solve square matrix problem by optimization. Is it possible? Okay, so now let me formulate an objective function phi which is E transpose E. Fine? I formulate an objective function E transpose E, and then what I do is, what is E transpose E? Ax minus b transpose Ax minus b, okay. And now I say that, well, minimize phi with respect to x. How do you get the minimum? First derivative equal to 0, right. So dou phi by dou x is equal to 0. Can you solve this? What will you get? If I solve this, if I use the rules of differentiation of a scalar function phi, is phi a scalar function? Phi is a scalar function, right? I am differentiating a scalar with respect to a vector. We have looked at the rules of differentiation of a scalar with respect to a vector. If I use those rules, what I will get is this equation: A transpose A x is equal to A transpose B. I will get A transpose A x minus A transpose B is equal to 0. This is the equation that I will get. If I differentiate and set derivative of phi equal to 0, I will get this equation. Okay? Is this fine? Just see this. You will get, if you expand this, you will get A transpose, you will get x transpose A transpose A x, then you will get A transpose x transpose into B. You will get 4 terms. You will get one term which is B transpose B. B is not function of x. B dou B transpose B by dou x is 0. Okay. So if you differentiate, you will very easily arrive at this particular equation. Okay. I just want to show that this is same as A transpose Ax minus B is equal to 0. Okay. Now if A if matrix A is non-singular. If matrix A is non-singular, okay, when will this be equal to 0? Ax minus b equal to 0. Okay, so actually by solving this optimization problem, you have reached the solution of Ax equal to b, and later at some point we are going to see a method for solving Ax equal to b using optimization, an iterative procedure which is faster in arriving at a solution many times. Then is this the optimum? Why is this the optimum? Why is this minimum? If you take second derivative, what will you get? A transpose A. A transpose is always a symmetric matrix. Whatever is A transpose is a symmetric positive definite matrix. Very nice matrix. Okay, so we have reached the minimum. Okay. Okay, so I can actually formulate a problem of solving Ax equal to b as an optimization problem. Yeah. This will be exact solution. Okay. Earlier we saw approximate solution. So in the situation where A is a tall matrix, okay, which means A is a non-square matrix. It has more number of rows than the columns. Okay, then you will get the least square solution. When A is a square matrix, invertible square matrix, this will give you exact solution. This will give you exact. Look here, no. This will give you exact solution. If A is invertible, when can you solve that problem? Ax equal to b when A is invertible. If A is not invertible, you cannot solve that problem, right? So now we are starting with the assumption that A is invertible, okay, and we want to solve the problem. So this obviously gives me the solution if I do this. Okay, so optimization could be a route to arrive at a solution of a particular problem. Okay, what I'm going to do for the case of boundary value problem is similar to the case where A is tall. Okay, so A is non-square. What I'm going to do for boundary value problem is qualitatively similar to A being non-square, that is A has more number of rows than the columns. Okay, it's possible to do, at least formulate the problem to get an exact solution of a boundary value problem using optimization, and that discussion is included here in the notes under the name of Rayleigh-Ritz method. It's very nice. You should read this section, though I am not going to do it on the board. It takes a lot of time, and this actually forms the foundation of finite element method, and finite element methods are very useful in solving partial differential equations. So I would say there are these two competitors. Finite difference is very easy to understand, but finite difference is not so efficient because you need large number of grid points. Okay, two methods that are competing, good methods, which balance between computational efficiency and good solutions, give you a good balance of these two things, are orthogonal collocation interpolation based methods, or these finite element methods. So now let's move on to boundary value problem. Okay, now I want to consider a specific problem here, boundary value problem. So there is some operator L which is operating on uz. Okay, I suppose now you are familiar with these kind of things because most of you are attending the other course on mathematical methods, and you have looked at these kind of problems, right? L operating on z, u of z is equal to this is equal to some fz, and boundary condition 1, this corresponds to u0 is equal to 0 and bc2 is equal to u1 is equal to 0. So this is a classical boundary value problem that you get when you are solving a partial differential equation. This will typically yield, if you solve it exactly, if you know the solution exactly, it will yield the eigenfunction expansions. Are you doing eigenfunction expansions? Yeah, so this will yield the eigenfunction expansions. Right now my mandate is not to solve it exactly, my mandate is to solve it approximately. Okay, I am going to solve it. Now here I am assuming that L is a differential operator which is operating on U. Conceptually we are not doing anything different than Ax equal to B, and we have talked about it, right. So this is equivalent to operator A x equal to B. We are trying to find out inverse problem, classic inverse problem. So right now I am not interested in the exact solution, I am interested in some approximate solution to this problem, and I am going to hypothesize a solution, approximate solution u cap z is equal to alpha 1. Okay, I am going to hypothesize a solution. Now what are these u1, u2, u3? These are some known functions. These could be simple polynomial if you want it that way, but you know polynomials is not a good choice. Okay, these could be Legendre polynomials, shifted Legendre polynomials. It could be sine and cos. It depends upon how you choose these functions. It's up to you, and you have to choose these functions such that the boundary conditions are met, of course. So I have these functions which I have chosen here. Let us assume that we have chosen these functions for the time being, okay, that such that at the two ends they satisfy the boundary conditions. Okay, we have chosen the functions such that at two boundary points you satisfy the boundary conditions. Okay, so you have to choose these functions in this particular case carefully. Now what I am going to do is I am going to define this residual. I am going to define this residual. Okay, the terms used are little different, but the meaning is same. In least square parameter estimation we call this error vector. Okay, here we call residual vector. Okay, residual is between left hand side and the right hand side. Okay, so the residual is between L uz minus fz. This is my error vector. In the case of finite dimensional least squares, what did we do? How did we find the minimum? Sum of the square of errors was minimum. What was actually sum of the square of errors? 2 norm square. What is 2 norm square? Inner product of the vector with itself, right? Inner product of vector with itself. So for the finite dimensional case, we had this. Just keep this in the background. In the finite dimensional case, we wanted to obtain theta. So theta least square was minimum with respect to theta, you know, inner product of error and error, right? Sum of the square of errors, least square estimation. Error vector was where error was defined as a theta u minus a theta, right? Just keep this in the background. Okay, I just want to do the exactly same thing here for this particular problem. Now I have this functions u1, u2, u3. So what I am going to do is I am going to pose this problem. Okay, I am going to pose this problem as minimize. I'm skipping the algebra, which can be a little bit tedious. I will write the final expressions, but whatever we have done till now, from that you can very easily derive what I am doing. If I have to do the same thing here, I'll have to write this as summation of these functions and then start working with those summations, and the expression will become complex, but that is just an algebra. The concept is exactly identical, so you should not. So what are the unknown here? What is the theta here? What is theta here? Alpha values, alpha 1, alpha 2, alpha m, right? Alpha 1, alpha 2, alpha m. Okay. Now what is RUZI? What is RUZI? Well, you will have to substitute one by one each. That is not the way to go about. Okay, so we want here RZI. Rather, what is RZI? What is RZI? RZI is L operating on summation I going from 1 to m alpha I UI UI of Zi. UI of Zi. Let me do a small modification here. Let us call this J. Let us call this J, and let us call this J. This is residual at. This is the residual at Z equal to. This is the residual at Z equal to Zi. Okay. This is the residual at Z equal to Zi. Well, do I need the points here? I'm not going to go same way as the grid points. I'm going to go in the parameter space directly. So what I'm going to do here is instead of forcing the residual to be 0 at each grid point, well, what I'm going to do here is to pose my problem as minimize with respect to theta phi theta, which is equal to inner product of R RZ. Well, this is something different from, okay, you should realize this. This is something different from, I'm not taking any grid points right now. I'm not taking any grid points. Okay. So what is this? What is the inner product? What is the inner product defined as? Inner product integral, say 0 to 1, right? Okay. Now, how do I get the equations from this? How do I get equations? I have to differentiate this. I have to differentiate this with respect to alpha, with respect to theta, right? So now what I have to do is to get the solution. To get the solution, I should see how many unknowns are there. There are m unknowns. I need m equations. Okay. So if my phi theta is this, then how do you get the optimum? Dou phi by dou theta is equal to 0. Okay. So which actually means dou by dou alpha I of R is equal to 0 for I going from 1 to up to m. Is this okay? Dou phi by dou theta equal to 0, which is same as, this is my objective function, error, right? This is my error square, sum of the square of errors, but it is not sum, it is integral of error. It is integral of error, not at one point, not at few points, but over the entire domain. Okay, there is a difference you can see here between what I am getting, the way I am constructing the solution, and finite difference method or orthogonal collocation method. Here we are setting this with respect to equal to 0. Okay, if I if I solve for this, okay, what do I expect to get? See, what is RZ here? So you have to actually solve this problem of dou by dou alpha I, okay, into what is this? This is Fz minus summation I going from 1 to m alpha I u cap I, right? What is RZ? RZ is Fz minus this, right? This equal to 0, okay, and this equation you have to solve for I going from 1 to up to m. Oh yeah, L of this, right, operator L operating on this, operator L operating on it, yeah. So thanks for this correction. So L operating on this and L operating on this, and I have to take derivative and set it equal to 0. But if L is a linear operator, if we make an assumption L is a linear operator, okay, then this alpha I will come out, and then you can differentiate and solve the problem very, very easily. So if L is a linear operator, then what I can do is, if I actually write those equations and collect the terms together, okay, I'll get this equation which looks very, very similar to the normal equation. You can work out the algebra, I am just skipping it, it's just matter of doing it meticulously. You will get this equation L u1 okay, you get this equation. If you rearrange, if you actually differentiate, do a little bit of take a trouble of rearranging all the equations and then put them together, you will get this equation which looks very, very similar to the normal equation, okay, except that operator L is operating on each one of those basis functions which we have chosen, okay, and then if I solve this, then I'll get alpha 1, alpha 2, alpha 3, alpha m. I am getting an approximate solution in the least square sense, okay. There is one difference here between the previous methods of discretization and this method of discretization. What is that? What is the difference? Here these integrals are over the entire domain, not at few points, okay. I am not evaluating this integral at few points, I am evaluating this integral over the entire domain, okay. So the finite dimensional approximation comes because of the finite number of basis vectors we have taken. The finite dimension business here comes because of, not because of the grid points, okay, not because of the grid points. Here you have constructed a solution which is not, see, in earlier case when you get the solution, you must have done it now for the boundary value problem which we are looking at, tram problem. It is some points, right, finite, after all you get only few points. Actually you know that the solution is a continuous function. By this approach we are getting a solution which is a continuous function. I will just take a simple example so that the ideas will become clear, okay. Is this algebra clear? Is there any doubt about this? See here L, this residual is Fz minus L operating on this function, okay, Fz minus L operating on this function. We are taking L to be a linear operator, okay, linear differential equation, and then we are solving this problem of estimating alpha 1, alpha 2, alpha m. Now let's look at a specific problem. Well, this particular method will work by this way because when the operator is linear, if the operator is not linear, what do I do? We'll come to that a little later. But right now we are just looking at the basis of the method which is least squares method, and the operator is linear, so we get this nice. So let's look at a specific problem, okay, that will give you better insights into. Well, I want to solve this problem of, my example is L uz, this is same as dou to u or d to u by dz square minus u equal to 1. So this is my fz, okay. I want to solve this problem, this is equal to 1, okay, over the entire domain this should be equal to 1, and my boundary condition 1 is u0 is equal to 0, my boundary condition 2 is u1 equal to 0. Well, u is not equal to 1, please note that u is not equal to 1. You are saying that this operator operating on u should be equal to 1, okay, do not confuse, okay. Now I am going to take a very simple solution to this problem. This particular problem, you must have seen in the other course that this particular problem can be solved analytically, you will get analytical solution. Right now the motivation is to convey some concept, okay, so that is more important right now. So let's take this approximate solution u cap z, okay. So my approximate solution is alpha 1 sin pi z plus alpha 2 sin 2 pi z, okay. Does this satisfy the boundary conditions? Satisfies the boundary condition at 0 and at 1 boundary condition is satisfied. Now I want to see if I get difference between finite difference method, okay, and this method is that if I get alpha 1 and alpha 2, I can find out value or approximate value of the solution at every point z, not at finite number of points. You get the difference? If I can get least square estimates of alpha 1 and alpha 2, I get, okay. So now what is the normal equation? The normal equation, so what is my u1 cap? What is my u1 cap z? Is sin pi z, and what is my u2 cap z? Sin 2 pi z, right? Sin pi z and sin 2 pi z, these are my u1 cap and u2 cap, right? Okay, what is the normal equation? What is the equation that you get? Well, normal like equation, let me not call it normal equation because not exactly the normal equation. So what is the equation that you will get here? How do you get alpha 1 alpha 2? So this is inner product of L operating on u1, L operating on u1 cap, inner product of L operating on u1, L operating on u2 cap, L operating on u2 cap, L operating on u1 cap, u2 cap, L operating on u2 cap. This matrix, okay, this matrix times into alpha 1 alpha 2, this matrix time alpha 1 alpha 2 will be equal to get alpha 1 alpha 2, what should this be equal to? Inner product of u1 cap 1, inner product of u2 cap 1. right? So what is inner product of L operating on U1? What is L? So let's go back here. So what I have to do, what is the first inner product? L U1 L U1. This is inner product 0 to 1. What is L U1? D by dz square of what is U1? Sin pi z minus d2 by dz square, right? d2 by dz square of sin pi z minus sin pi z, this right. So this integral I can do, I can just, it's not so difficult to do this integral. You have to be a little bit patient and then do these integrals. Okay, if you work out these integrals, okay, well, I'll write down what you get here. Actually, just if you take this, what you can show is that L U1, this is equal to minus pi square plus 1 sin pi z. You can show this very easily. You can also show what is L U2, okay, and then you just have to find those integrals. If you find those integrals, what you see here is you will get pi square plus 1 whole square by 2, 0, 0 and 4 pi square plus 1 whole square by 2. Right hand side will turn out to be minus 2 pi square plus 1 by pi and 0. If I do patiently all those 4 integrals, okay, then I get this equation. I have chosen orthogonal basis functions here. Sin pi z and sin 2 pi z are orthogonal, so that helps me in this particular case, that helps me in getting these to be 0. This comes out to be a diagonal matrix, and what happens here is that I get the final solution. So what is the final solution? If I compute alpha 1 and alpha 2, I get the final solution to be, my solution comes out to be minus 4 by pi square plus 1 sin pi z. So which means alpha 2 comes out to be 0, alpha 1 comes out to be this, and this solution is pretty close to the, in this particular case the true solution can be found out. The true solution is uz equal to, this is the true solution, this is the approximate solution. True solution can be found by some different means, not by this approach. Yeah, and then force the residual to 0. So now here I choose some of these functions from a standard basis, no? I can choose them from a standard basis like sine, cos. I could choose them from Legendre polynomials, shifted Legendre polynomials. I could have worked out this problem using shifted Legendre polynomials if I have those shifted Legendre polynomials which satisfy the two boundary conditions. In this particular case, sine functions are convenient because they satisfy the two boundary conditions. They may not be orthogonal, but in this particular case, orthogonality always helps. We always work with orthogonal functions. Okay, we try to work with orthogonal functions as far as possible. Orthogonality is, but this solution, there is one difference between this solution and other solution. Other solution is exact at known points. Exact means it is not exact, it exactly satisfies the differential equation at known points. Here this solution is obeying the differential equation in the least square sense. Okay, at every point it's not equal to 0, but if you take the least square sense, it is 0. Okay, integral of the square of error is 0, error is not equal to 0. Okay, integral of the residual square is 0. Okay, even in the other case, we are forcing residual to 0 only at finite points. What happens to the residual at the points which are in between? They will not be 0, right? So we are only forcing at a finite number of points. Even here, you do not know which points exactly the residual will be 0, but the solution will be crossing 0 at many points. So this is both are approximate solutions. This is one way of getting approximate solution, and you have another way of getting approximate solution, which is what we have seen earlier. Okay. Now the problem is that in everywhere where you are solving this, your L will not be in general. It will not be linear. There could be a non-linear differential equation. We are solving this tram problem, right? It's not a linear operator. Okay. So what do I do? What will I get? How will I solve that problem? So in that case, I just use the concept of orthogonality between the subspace and the error, the concept that we had earlier, and we'll get the method of Galerkin method. So I will discuss it briefly in my next class. But the next class, after doing that half an hour of Galerkin method, something about a Galerkin method, I want to move on to solving problems, because we are only 2 classes away from the end sem and then mid sem, and we'll solve some problems of least square, so that you get better insight into what is happening. But the key thing here is that right now I have not used polynomial approximation, I have used general function approximation. The solution is obtained by posing the problem as a least square problem, okay, and then you are getting a solution, approximate solution of the boundary value problem using least squares approach. Okay, it's possible to extend this to partial differential equations. We'll have to compute double integrals in x and y and so on. Okay, it's possible to do that in algebra will become complex. The concept is not different.